Due to the widespread experimental evidence of anomalous diffusion, there has been a huge mathematical effort and theoretical effort to develop models that could somehow describe and predict this behavior. There is a wide zoology of models that can explain anomalous diffusion. Some of them are ergodic, some others predict ergodicity breaking in some conditions. But in this this big literature, we will only focus here on two of these models, namely the fractional Bernal motion and the continuous time random walk. The fractional Bernal motion can be obtained starting from the Langevin equation that we have seen earlier, in which we modify the noise term, the terms that take into account the fluctuation due to the interaction of a particle with the environment. This noise is basically uncorrelated. Here we have a correlated noise, and the correlation has a power law with respect to the difference of times. If we solve the equation and calculate the 2-point correlation on the positions, we see that also the position of the particles at different times are correlated. So this breaks one of the three assumptions in the theory of Einstein. So assumption 2 is broken, so the motion is not Brownian anymore. And this produces the change of behavior in the mean-square displacement. In this case, we have to distinguish, as always, the case of subdiffusion and superdiffusion. That depends on the value of the exponent alpha. But in this case, it also has a meaning in the sense that when we have subdiffusion, there is a negative correlation in the 2-point correlation. And in the case of superdiffusion, this correlation is instead positive. And from the experimental point of view, this model has been used to explain several behaviors, in particular in cytoplasm of the motion of particles in the cytoplasm of living cells, and is associated in general to the description of viscoelastic media. Here we just represent the typical trajectories obtained by simulations of fractional Bernal motion. And here we have the corresponding ensemble average mean-square displacement, in which we can see actually several things. I mean, of course, we see that the scaling of the ensemble average mean-square displacement is proportional to the time to the power of alpha. But we see that this is true only in a range. And if we compare it to the time average mean-square displacement, we see it even better. I mean, there is an initial range of times in which, time lags in this case, in which the behavior is different from the expected scaling, and you reach the expected scaling only at larger times. And the other thing that we can see from this plot is that for its for the same definition, the time average mean-square displacement has less statistics at large times, and this depends on the finite length of the trajectories. So this is something that produces some sort of scatter, some sort of noise in the last point of these curves. Still, we can see that both the scaling of the ensemble average mean-square displacement and the one of the time average mean-square displacement in the range in which, after the transient and in the range in which we have good statistics, they follow the same scaling law with the alpha that that was imposed in the simulation. So the model is ergodic. The other mathematical model of interest that has also been widely applied to describe several systems is the continuous time random walk, or I would have to say a special case of continuous time random walk, because continuous time random walk is a very wide framework that includes several possibilities. In general, one considers continuous time random walk every model in which there are displacements of the difference in position of the trajectories that follow some distribution, and that are sampled at times that are also drawn from some statistical distribution. In this specific case, we consider only a subdiffusive kind of continuous time random walk, in which the displacements are extracted from a Gaussian distribution, And the waiting time, so the time between changes in position that we simulate, are extracted from a power law distribution that associated to the power alpha, that, as we will see, will govern also the mean square displacement. The continuous time on the work, as we have described it in this example, also breaks one of the assumptions of the theory of Einstein. And in this case, not the third one, but not the third one as we described it earlier, but is in an extended version, because the assumption 3 of the Einstein theory, as we described it earlier, it's applicable only to the case in which the sampling time is constant, so that the position is sampled at regular times. But in the case of the continuous time on the work, this is not true anymore, because we can sample the position at different times, at the times that are extracted from a distribution. So in this case, in order to have Brownian motion, we not only have to require that the variance of the displacement is finite, but also that the mean of the current waiting time is finite. If this is not the case, as we see in here for the choice of the distribution of waiting times, then the motion is not Brownian anymore and leads to anomalous diffusion due to this continuous time on the work model. As we will see in a second, for some in some condition, the continuous time random walk also verifies weak ergodicity breaking, meaning that the scaling of the time average and ensemble average mean square displacement are not the same. So according to this recipe for simulation for the generation of trajectories performing continuous time random walk, we have trajectories that in general look like this for a fixed exponent alpha. And then if we calculate the ensemble average mean square displacement, we see that expectedly it follows the power law scaling that we impose in our model. But when then we turn to the time average mean square displacement, we see a few interesting things. First of all, the amplitude of the mean square displacement curves, even at the same time lag, varies a lot. And this scattering is associated to the fact that mean square displacement continues to be a random variable, even for long trajectory times. And this is associated to the weak ergodicity breaking property. And actually, we can also see, just to show that this is indeed the case and there is a weak ergodicity breaking, that the scaling of the time average mean square displacement does not follow the power law behavior that we would expect. In the case, this would be an ergodic model, but we can see that this scale nearly linear in the range in which the noise is low due to the finite length of the trajectories. So continuous time random walk breaks ergodicity and breaks it in the sense that we described earlier from the single particle point of view. The time average mean square displacement is a random variable even for long recording time, even for long trajectory times, and the scaling of the time average mean square displacement is nearly linear, whereas if we look at the ensemble average mean square displacement, it scales as a power law with the exponent alpha. After talking about what anomalous diffusion is and what weak ergodicity breaking is, let's just start to explore some ways to detect and quantify this phenomena. We are interested in a very general problem, which is starting from a trajectory, determine if it is a Brownian trajectory or not, and this is somehow associated to determining the anomalous exponent associated to this process. And of course, these implicitly also solve the problem of determining if it's Brownian or not, because an alpha, an exponent compatible with 1, will automatically classify the trajectory as compatible with Brownian diffusion. And if it's not, by determining exactly with or with high precision this exponent, we can understand more about the motion that is taking place. From what we have seen, the information about the anomalous exponent is contained in the mean square displacement. So it might be straightforward to think that if we calculate the mean square displacement, either the time ensemble version or the time average version or the ensemble average version, we can perform some kind of fitting of the curve to determine the alpha. Actually, due to the power law form of the mean square displacement with respect to time, we can take the logarithm of both sides of the equation. And in this case, we see that the logarithm of the mean square displacement behaves as a straight line with respect to the logarithm of time, or time lag if it's the time average version, where the slope is exactly alpha. And the offset is related to this constant that has the units of equivalent diffusion, equivalent diffusivity. Because it's diffusivity, but due to the alpha exponent, does not has the typical dimension of a square of a length over time. But although this procedure might seem straightforward, it's kind of tricky for several reasons. The first reason is associated to the choice of the fitting range. In this example that we are showing, we have a mean square displacement corresponding to fractional Brenner motion with a ground truth anomalous exponent that is equal to 0.85. If now we perform the fit according to the straight line of the logarithm of the mean square displacement with respect to the logarithm of the time, we retrieve an exponent that is much lower. And this is due to the fact that, as we already mentioned before, we do not have the same number of points for calculating the mean square displacement at each time leg. And this is due to the limited length of the trajectories. Of course, at large time lags, we have less points on which we can average, and there is more scatter. So before performing this the fit, we might need to somehow choose a range of time lag where to perform it. But this is not trivial because it depends on several conditions. And actually, there are several papers that try to address this issue. A rule of thumb that works quite well in many cases is to consider only the 10% of the points in the mean square displacement curve with respect to the length of the trajectories. For example, here we are considering a trajectory of 500 points, 500 time steps, and in the first case we perform the fit over time lag up to 300. But in the second case, we limit the fit to time lags up to 50, which is 10% of the total trajectory length. And in this case, we can see that there is a considerable improvement in the values that we obtain for the alpha, although it's not exactly the true one. There is also another factor that needs to be taken into account when we perform this kind of fitting, which is related to the presence of noise. The trajectory that we have generated that is represented here in blue comes straight from the Langevin equation. But sometimes, in particular in experiments, we have addition to the real movement of some error, for example, associated with the localization precision, the precision for which we can detect the position of the particle at each time. And to show what is the effect of this noise on the mean square displacement curve calculation, here we are just adding in orange to the original trajectories a Gaussian noise with zero mean and with a standard deviation of 0.1. we see that the major characteristic of the trajectory do not change. But when we calculate the time average mean square displacement, we see that it is shifted up, and it's shifted up by a quantity which is proportional to the variance of the noise. In principle, it does not seem to be a big deal, but it does because it changes the form, the expression of mean square displacement with respect to time by adding this constant, this due to noise. Therefore, if we try to apply the same fit that we had performed before after the logarithm transformation, we do not exactly retrieve the value of alpha, but we retrieve a value that now also depends on noise and leads to a sub-estimation of the correct value. Actually, this is a quite common error, and many people suspect that several Brownian trajectory has been reported as anomalous only because of not taking into account the value of the noise and the effect that it has on the mean square displacement. I mean, in this case, we see that this fitting is performed in the same condition as this one, so using only the first 10% of the points, but still produce a quite large. I mean, considering that also the noise is quite low here, the effect that we see in the determination of alpha is quite important. To prevent this issue, there are first possibility is to estimate the noise independently. For example, one possibility is to record the motion of an immobile particle in the same setting as a mobile one, and once we have a value for this standard deviation of the noise, we can just subtract it from the mean square displacement curve. Otherwise, one can try to make a nonlinear fit with taking into account a value of another constant, which will be exactly the one corresponding to the noise. But this is not recommendable because there is correlation between the values of the variable in the fit. Another property that one is interested in obtaining from the calculation of a single trajectory is associated with its ergodicity. For example, one would like to know if the set of trajectories that you obtain from these experiments are ergodic or not. And this is strictly related with what we just said, because the definition itself of ergodicity, of non-ergodicity, of weak ergodicity breaking, concerns with the different scaling of the time average and ensemble average mean square displacement. So one might just think of getting a bunch of MSD curves from the time averages, feed them, and compare the exponent or the average of the exponent that you got with the exponent obtained from the fit of the ensemble average mean square displacement. This is a possibility, but a more quantitative way of doing that corresponds to the calculation of the so-called ergodicity breaking parameters. The ergodicity breaking parameter tells something about a concept that we described earlier, which is the fact that in a non-ergodic system, the time average mean square displacement is a random variable no matter how long the trajectory is. And actually, the ergodicity breaking parameter is estimated as the average of the square of the time average mean square displacement at a given time leg divided by its average, squared, which in this case we call the time and ensemble average mean square displacement, which basically, as we can see from the formula here, corresponds to calculating the time average mean square displacement for all the trajectories and then average them all for each time leg. So this ratio -1 gives us the ergodicity breaking parameter, and we can expect that for an ergodic process, it goes to 0 as the length of the trajectories increases. So basically, this quantity is calculated for specific time legs, but then we look at this evolution with respect to the length of the trajectories. In a typical experimental setting, one where this t cannot be made extremely long, one can actually try to calculate it by cutting the trajectory at a specific length and getting the trend of this quantity over time. And here we just calculated it for the two models that we explained earlier, which are the fractional barrel motion and the continuous time random walk. And we calculate this quantity for three different time lengths, in this case 2, 10, and 20, for trajectory that are 500 time steps. And we see that actually, as expected, for the fractional barrel motion, which is ergodic, we see a convergence to zero of the ergodicity breaking parameter, which is faster for short time lengths, is lower for longer time lengths. But in the case of the continuous time random walk, we actually see that this parameter does not converge to zero, at least in this range. But actually, this for the continuous time random walk case, it can be calculated analytically, and it has been demonstrated that the ergodicity breaking parameter converges to a finite value that depends on alpha. So by means of this parameter, we can have an alternative estimation about the ergodicity property of our experiment or of our system. I would like to stress that something, which is that, I mean, no matter if we calculate the ergodicity breaking parameter or the difference in the scaling of the two averages of the mean square displacement, we are still doing this estimation from an ensemble of trajectories. None of the two approaches allow us to determine the ergodicity from a single trajectory. For doing that, we need other estimators. For example, in the notes associated to this with this class, I describe one. Due to this limited amount of methods to explore the ergodicity from a single trajectories, a few years ago, together with some colleagues, we started wondering if it was possible to apply alternative methods. And since we were all very interested in these new methods that were coming from the world of artificial intelligence or machine learning or deep learning, depending on the category that you want to consider, we started thinking, is there anything that we can do in order to train a machine to tell us something about the, for example, anomalous diffusion or the ergodicity of a trajectory? And this discussion was very interesting. It took quite long. Many other people were involved. We collaborated with several groups. About a year, between 3 years ago and this year, several papers were published with new methods to do similar approaches, for example, to determine the anomalous exponent or to classify trajectories. And we finally decided that this popularity of this subject deserved to the organization of a challenge to assess the performance of these methods and to also foster the creation of new ones. So nowadays we have several methods that are able to solve different problems from the single trajectory point of view. These problems, if we consider the one that we included in the challenge, we can divide them in three categories. The first one is the regression of the exponent, of the anomalous diffusion exponent alpha. The other one is the classification according, for example, to the model. As I said before, that besides fractional barrel motion and continuous time random walk, we have other diffusion models that also produce anomalous diffusion. Classifying among these is another task that was included in the challenge. And the third one is to segment the trajectory that undergoes changes of either the exponent or the model, or both. As an example, here and in the exercise that you will find on GitHub, I describe a simple system that can perform this kind of operation, which is a convolutional neural network. When analyzing the results of the challenge, we saw that several deep learning architecture can perform really well on these kind of problems. This is probably not the best, but it's a very simple one that performs reasonably well and takes as an input the coordinates of trajectory. Here we're considering a simple 1D case, as in many of the other examples we discussed so far. So we have a position of a trajectory sampled at different times. And since many of the properties that we want to determine are associated somehow to a short time correlation between a position and the next or the previous or the ones, in this case sense, the convolution allows us to extract features from this kind of local properties. So basically, this network is composed. The architecture of this convolutional neural network is composed by uh, three convolutional blocks with different number of kernels that calculate these features. So basically, from here we have uh, several features coming out from a single trajectories that then to them we apply an activation function. In this case, in these three cases, it's a rectified linear unit and some batch normalization. And then we sequentially apply these blocks with different number of kernels. And then the output is sent through two dense layers that basically extract a specific number of features that are then combined to get as the output of the network. That, depending on the problem that we want to solve, might be a single value corresponding, for example, to the anomalous exponent, or a class, a probability of belonging to a specific class. In the example that we discussed in GitHub, might be ergodic, non-ergodic. I must say that in the case, in the example that we show, the classification between ergodic and non-ergodic exactly correspond to the classification between fractional random motion and continuous time random walk. But it might be further generalized just by including further models, either ergodic or non-ergodic, in the training dataset. And for the training, we have developed a library, a Python library, to simulate trajectories of a specific length or belonging to a specific model with a full range of anomalous exponent as we want, that you will also explain in the exercise how to use. So this is an example that, as I said, performs quite well on these two problems, the regression, the inference of the anomalous exponent, or the classification of trajectory between ergodic and non-ergodic. And I invite you to play with this example that's there. Not only needs to be trained, and then you can probably try to change the hyperparameters of the network to see how it works, and see how the results are influenced by the different choices. There are two interesting aspects associated with the use of deep learning methods for solving problems associated with anomalous diffusion on the single trajectory levels. The first one concerns the inference of the anomalous diffusion exponent alpha. Because basically what we have seen is that with the proper training, these kind of architectures are able to also learn information about the noise for each trajectory. And so these directly solve the problem that we have seen before, that it was associated with the fit of the mean square displacement, of the time average mean square displacement. Of course, there is a dependence of the performance of the method for, in particular, with the accuracy of detecting this exponent. It also depends on the trajectory length. But still, the performance are quite impressive, because it has been shown that we can detect the exponent with fairly good precision, even for trajectory as short as 10 points. The second interesting aspect is associated with this ergodic non-ergodic classification. As I said earlier, there are very few methods that allow us to detect ergodic properties at the level of a single trajectories. And moreover, these methods are asymptotic methods. It means that they often require very long trajectories in order to be able to tell if a trajectory is ergodic or not with a good confidence, with a high confidence. In this sense, these deep learning methods provide a further tool that is able to solve this problem. So I guess we have arrived to the very end. I just want to remind you that this is the web address of the exercise on GitHub. There is a Python notebook. Please feel free to play with it and enjoy. And we will see each other soon for further discussion. Thanks for your attention.